Slope field. So I am going to introduce kind of not a new idea, but a little twist on what we already know. Slope fields. Good stuff. Slope fields. So the idea, remember, dy dx. What did dy dx mean? The derivative. What's it called what's the equation called when you have a dy dx in it? No. When there's a y prime or a dy dx, what kind of equation is that called? What's the word? We just talked about the other day. Differential equation, right? So if you have a differential equation, that equation with the derivative in it, tells you what about your original function? It's the rate, but just basic. It's the what? It gives you the slope, right? So if we look at a differential equation, we can determine the slope. Differential equation gives you the slope of the original function. So when you take the antiderivative of the differential equation, what do you have to include to get the original function? The plus c, right? That equation with the plus c is called the parent function. General solution, yes, it's called the parent function. Okay? Now what's the difference between the parent function or the general solution versus the particular solution? There's an infinitely many solutions that match that general solution, right? So a parent function has the plus c in it, and that plus c represents what? The vertical shift, and we don't know what that vertical shift is, right? So what we do is we try and understand what the original curve looks like by looking at slope fields, okay? And the way we know the actual solution is the initial condition. I'm going to give you a very basic idea or basic example, and then we'll dive into it a little bit more. Okay. So how do we know what the original graph looks like? If I give you dy dx, I say dy dx equals this. How do you know what the original function looks like? Take the integral, take the antiderivative, and you know what it looks like. You just don't know how high or low it is, right? Okay. Are you capable of taking the antiderivative of every function? No. So we have to look at slope fields to be able to analyze what it looks like, because we can't take the antiderivative of everything. Okay? So what a slope field is a graph that just has a bunch of small linearizations. What is a linearization? Okay, we use it to approximate, but what is a linearization? This is a problem you had a hard time with yesterday. Linearization just means tangent line. That's all it means, right? So basically what we're saying is, I don't know what my curve looks like, but if I know the slope at this point, maybe the slope is like -1. So I can just put a little linearization, a little line, a little tangent line that has that slope. And then maybe the slope here is 0. And then the slope here is maybe -1. And the slope here is -2. You can kind of get an idea of what the graph looks like, right? You can kind of connect them. Now, is it guaranteed? No, we don't know what's happening in here in between. So if you want a more accurate slope field, you would plug in another point in between, right? And so you get that. I didn't catch that. I don't know. Okay? Now, again, that's not a guarantee, but that gives you an idea. It gives you a trend of what's happening. So let's look at an example that we can actually take the antiderivative of. If dy dx equals cosine of x, graph a slope field. Well, we could graph it. We could graph this function. If dy dx equals cosine of x, what do I do to solve the differential equation here? Yeah, the process, right? Remember the process we talked about? Got to multiply by dx and then integrate. So we get y equals, what's that? Sine of x plus c, right? So when we go to graph this, the parent function is basically the home function. So sine would look like this, yeah? Okay, and then back this way. But is that the actual graph? No, that's what it looks like, but we don't know where it's at. So you could have one that looks like this, or one that looks like this. You guys okay with this? Okay? But I want to show you what it looks like on a slope field. Okay? So what I'm going to do is I'm just going to plug in coordinates to figure out what the slope is. So what's a good coordinate to start with? 0, 0. Okay. So if I plug in 0, 0, that means x is 0 and y is 0. So if I plug in 0, 0 to this, what's the cosine of 0? 1. Cosine of 0 is 1. Notice I didn't have to plug in y, because there is no y, right? It doesn't matter what y is. In other words, y could be anything. So if x is 0, then the slope is what? 1. So we just plot little tangent lines that has a slope of 1. Well, the reason it can be along the whole x-axis, because if I plug in, like right here, 0, 2, if I plug in 0, 2, where's the y that I would plug into? Where's the y here? There isn't one, so the y value doesn't matter. The x value does in this case.
Why do you take the antiderivative for moving values to?
I'm showing you the relationship between them. What is this finding here? What is dy dx? When I plug into this equation, what am I finding? I'm finding slopes, right? Because that's the derivative. So I'm just drawing little lines with those slopes, little tangent lines with those slopes. I'm just showing you how it's going to relate to this because I can take the antiderivative, right? You'll see what it looks like. What's another one we could pick? Yeah, what cosine value do you know? Pi over 2. How about pi? When x equals pi, what's the slope? Cosine of pi is -1. So at pi, we're going to go down 1. Or not down 1, but the slope of -1. You guys okay with this? What's another one we know? What would you say? Pi over 2? What's cosine of pi over 2? 0. Okay, so cosine of pi over 2 is 0. So the slope at pi over 2 is 0. Okay, maybe another one, 3 pi over 2. What's the cosine of 3 pi over 2? 0. So the slope is 0. And then we can keep going with this all day long. Okay? But watch what happens as we do that. If I try and understand the trend, it doesn't matter where I start. If I start here, if I go along my little tangent line, and then what's this tell me to do right around here? It tells you go down, and then you go down, and then it tells me to go over, then it tells me to go up, and then it tells me to go over and down, right? So if I follow that trend, you see that? Do you see the tangent, or do you see the original, or the y function in there? Right. You guys okay with that? Now a slope field is not the lines. Or the slope field is not the curve. The slope field is just the little linearizations. That's the slope field. Okay?
So we have to make specific graph for this kind of thing.
Basically, yes.
Are they going to ask us to make a graph of this thing? Is that going to be a question?
It'll say graph the slope field for the given indicated points or something like that.
I don't mean to sound like that, but what's the point of that?
That kid. The point is, in this case, I could take the antiderivative, and because I can observe the function, I know what the function will look like in general, right? And this is a basic example. But what happens if I give you a function that you can't take the antiderivative of, and I say, what's it look like? You're going to, I don't know. So you do a slope field to see what it looks like. And you'll see I'll give you an example in a second. But really what it comes down to, what if I said dy dx, for example, equals 2x, this might be a common one, 2x over y. Do you know how to take the antiderivative of that? No. So do you know what this looks like? Not a clue. So therefore, I say, what's it look like? You're going to have to do a slope field to determine that. Right? All right. Can I go on? So let's take a look at a little bit more in-depth problem. What's the difference between this differential equation versus that differential equation? There's a y value there, whereas that one didn't, right? So let's see here. If dy dx equals x plus y, I want you to construct the slope field at the indicated point. So how many points do we have to evaluate?
4, 5, or 0?
Only 5 points? 25 points.
Oh wow, that even.
I need the slope at every point, every red dot basically. Okay? So what I'm going to do is I'm going to create tables to try and get an idea of what this looks like. So I'll create a table. It's going to be a really big table. So what does this mean? I'm going to pick an x value, pick a y value. That's the coordinate I'm talking about. And when I plug these values in to dy dx, if I plug those in, what am I finding? I'm finding the slope. That's why the m is there, right? You guys okay with this? Okay, so what's a good coordinate we want to use? 0. How about 0, -2? If I plug in 0, -2, that means I'm finding the slope at this point right here, right? So what would the slope be at 0, -2? I'm just plugging it into the derivative function. X is 0, y is -2, so 0 plus -2 is -2. No, I picked it because it's on the grid. I got to find the slope there. Yeah, you could start anywhere. It doesn't matter. I picked that because I'm going to go in a pattern. So I'm going to keep all my x's 0 and then just move up the y-axis. 0, -1, what's the slope? -1. Okay, 0, 0. 0, 0, 1. 1, 0, 2. 2. So now I have all the slopes that I want along the y-axis, right? So what's this slope going to be? It's going to be -2, so kind of steep. And then this slope here is -1, so it's not as steep, and then so on and so forth. Does that make sense? Okay. 20 more to go. So let's pick like 1, -2. What's the slope at 1, -1, -2, I'm sorry. What? -3? -1, -1. -1, 0. -1. Well, we're just adding them together because it says dy dx is x plus y. You're gonna just plug these values into the x and y values in the differential equation. So -1, 1 is 0. -1, 2 is 1, right? And so what do we notice about this row of slope fields? This one is what? It's steeper than what it was before, right? And this one is what that one was, right? Oh, that's -1. I'm sorry. Back the other way. You guys okay with this? Fill out the rest of them. Give you a minute to do that.
That's more like it.
Okay, so pick -2. I'll give you more practice. You guys have more practice on your paper there.
So when we're drawing the lines, are we just estimating about how steep it is?
Yeah, so you don't want, if the slope is -2 at a point, and then it's -3 at another point, you want to make sure the -3 is steeper than the -2.
Well, so when something rare like this, would it be like an FOQ or would it be like a multiple choice or something?
I've seen it both.
So if it was in the form of an FOQ, would they give you like benefit of the doubt if it didn't look like a -3 slope or a -2 slope?
Yeah, they're not going to go, oh, that's actually a -2.25, not a -2, so minus a point. No. Generally, when they go to grade it, it's, did you get the slopes right on the 0 ones? On the slopes that were 0, did you get those right? And did you generally get the idea of positive and negative slopes? And, you know, is this one steeper than this one because it was supposed to be? No.
Do they want us to draw lines, like to connect them, or do they?
No, the slope field is just the tangent lines. Okay. And usually on the AP exam, there's not 25 points to fill in. It's like maybe 9. It's like 3, 3, and 3. Maybe, it depends. It could be 12, but never 25. I've never seen 25. On a multiple choice question, it looks like the ones that I gave you there. All right, so that's the slope field, and this is what's interesting, okay? Because the differential equation has x plus y in it, if I were to draw the parent function, it will be different depending on where my initial condition lies. You see, if my initial condition lied at, let's say, negative 2, 1, if it started here, if this was my initial condition, what kind of function do I have? I have a linear because I'm just going to trace down like this. Oh, down, down. These all have a slope of negative 1, so it's probably just going to be a line. You get what I'm saying? Whereas, if I have an initial condition of, let's say, 0, 0, what's that going to look like? Kind of exponential, but when I go backwards, what's it telling me to do? Going back up. So it's going to do something like this. It's going to go down and then up, and then it's going to get really steep going this way. You see the difference there? Okay. Versus if I pick a point over here, then it's going to, like if I pick this point, it's going to go down, and then it's going to keep getting what? Steeper this way. So depending on the initial condition, your function is completely different, because you agree all three of those examples I gave you are completely different graphs, right? One was a line, one was kind of exponential in a way, and the other one was kind of logarithmic or something. I don't know. But isn't it interesting that if it was up here somewhere, what would you call this line here? This is almost like an asymptote. Right? It's not a horizontal asymptote, it's not a vertical asymptote, it's a diagonal asymptote. Right? Because if it crossed over here, then it falls into a different set of rules for the differential equation. Okay? Are you guys okay with this? Okay. That's it on that. So you got a half sheet of paper with 4 questions. I'm going to give you 10 minutes to work on it, and then I want to go over the FRQ that you were supposed to finish at home. And then whatever time we have left after that, you can finish this up. Okay? But work together on this if you need to. Make sure you're understanding it. You don't graph it. It doesn't exist there. You could say it's infinity, right?
Okay, so how do you draw that?
But it's not actually infinity. It would be infinity if we're approaching that value, right? The closer and closer we get to x equals 0, the closer and closer it gets to a vertical line, right? But at 0, in a sense, it's a vertical asymptote.
Okay.
You don't draw it. You just leave it blank. Okay, so here's how I would approach this, and maybe I should bring that up. No, I just wanted to show you this. Let's see here. Slope fields. Okay, so looking at the first one, there, you should have, what is it? It just kind of, oh, they're diving down, right? So they're kind of doing this, if you're visualizing the functions. And you have maybe a vertical asymptote at 0, at x equals 0, because you can't divide by 0, right? Here, this looks kind of like a what? Looks kind of like a circle. That's interesting. Here's how I approach these problems. The first thing I try to do is identify when the slope is going to be 0. When is the slope going to be 0 on number 2? Whenever x equals 0, the slope is 0, except for one case. So I draw a bunch of tangent lines when x equals 0. Okay? Let's see if I can do this. It'll let me. So here, 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 here. Why didn't I put it at 0? Because that would imply that y is 0, right? And what do we notice about when y is 0? Well, it's not indeterminate because we're not taking limits. We're dividing by 0. When y equals 0, what do we get? Undefined, right? So when y equals 0, you might want to think about drawing vertical lines, but there's nothing there. So that's that. So I ask that. I say, when is the slope 0? Those points. Hey, come on. When does the slope not exist? When does the slope not exist? When y is 0. So along here, the slope does not exist. Here's the next question I ask. When is the slope positive? When is the slope positive? Say it again. When one of the values is negative, when the x value is negative and the y value is positive, or when the x value is positive and the y value is negative, right? Which would be in quadrant 2 and quadrant 4. So in these quadrants, we have positive slopes, whatever they are. And then when is the slope negative? The slope is negative when x and y have the same sign, right? So then that would be in quadrant 1 and 4. So that's a very rough slope field, but it gets you to eliminate, if it's a multiple choice thing, it gets you to eliminate a bunch of things really quick. Does that make sense? Okay. Number 3, same question. When is the slope 0? When y is 0. It looks like it does not exist here, but you can kind of see the trends. Is it getting steeper or shallower? It's getting shallower, right? It's becoming flat. And so you can kind of see a little bit that there's little blue lines there. Kind of. It's hard to see, but that's because they're the same line. Anyways, when is the slope infinity? As what happens? When does the slope become vertical? When does lines become vertical? When the y value gets really big, right? Or really small. So what is determining the slope here? Strictly what value? Just the y value. The x value has no effect on this. So you can cross out a. Oops. Okay. You can cross out a and d, or a and c, because c is just a constant, right? It just slopes of 1 everywhere. So now, which one of these, as y gets bigger and bigger and bigger, makes the slope steeper and steeper and steeper? The y squared, right? If y gets bigger and bigger and bigger here on c, what's happening? Yeah, as the bottom gets bigger, the number gets shallower. So that's out. So D is the answer on that one. Okay. When is the slope positive on number 4? Sorry, let me rephrase that. When is the slope 0? When x and y have the same values, right? So when x and y hold the same value, you get 0. So in other words, when x equals y, that implies the slope is 0. So which one of these options would kind of show that x and y would have to be the same to get 0? B, because 3 minus 3 is 0, right? Is there any other ones? No, that's kind of out. And then my next question, when is the slope negative? This is an interesting one. When is the slope negative? All up here, right? Well, when x is negative, y is, well, it's down here when x is negative and y is negative. We know this is the answer, right? When is there a negative slope? When y is greater than x. And when's it positive? When y is smaller than x. So when x is 2, anywhere x is 2, y has to be smaller than 2. So here's when y is 2. So anything below that, you're going to get positive values. Anyways, so it's just kind of, yeah, it's a little bit of a guess and check type of thing, but that's what it is. Get your free response question out from yesterday. And let's just put your answers up here and see what you got here. Grade yourself. Hopefully you did this with a little bit of integrity, right? And then you can really see where you're at. Let's see, part A, g of 0 was 9/2. G prime of 0 was 1. And you get 1 point for each one of those. Okay, B. G has a relative max at x equals 3. Notice it said relative. So the justification for that is just when, what? G prime does what? Changes from positive to negative, right? Now, and it was an open interval too, right? Am I right on B? So you didn't even have to consider endpoints on that one. So G has a relative max at x equals 3 because G prime, which is equal to F, changes from positive to negative. You get 1 point for the correct answer, 1 point for the correct justification. All right, C. The only x value where F changes from, that's interesting, okay. What was it asking for in C? The absolute minimum, right? Because instead of showing why 5 is a maximum, they just said, I'm just going to shortcut it and evaluate it. Because here's the thing. the absolute minimum has to occur at a critical point, right? And since when x equals, what is it, -5? That's a critical point. It's not a minimum, but it's a critical point. So they said, instead of figuring out which ones are maxes and minimums, I'm just going to evaluate all critical points.
So if we can do -5 is not.
No, but you have to kind of justify why it's not a minimum. You'd have to eliminate it as a possibility, basically. Okay? So you're, what? Identify x equals -4 as a candidate. G of -4 is -1, and justification in your answer is the third point. And then part D, what was part D asking for? Points of inflection. Points of inflection occur when G double prime changes. G double prime changes signs. That means G prime changes direction. What is this graph of? It's graph of F, but what's F equal to? G prime, so we're looking for when it changes direction. Happens where? -3, 1, and 2. So how do you grade that? You get 2 points for having all three, and then you subtract a point for every one that you're missing. So if you got 1 out of the 3, you got 0 points. If you got 2 out of the 3, you get 1 point. If you got 3 out of 3, you get 2 points. Does that make sense? And if you have more points than those 3, then you got to subtract a point for every point you have additional.